Hello, Professor and TA. My name is Sahil Chitnis, and today I'm going to present my midterm section of my systems engineering project on the development of global positioning systems, that is GPS. We will understand how the US Department of Defense developed this huge and complex system with the help of system engineering principles from its initial phases in 1960 to its full deployment in 1995. We will start from the initial phases of proposal slash conceptualization and go through its development, production, and deployment to full working capacity. Before beginning the presentation, let us go through a list of topics that I will be covering today. Firstly, we will be looking at a brief introduction to the systems engineering process, followed by a brief introduction of the global positioning system. We will then be going through some of the GPS history and through the various system engineering phases. The first phase will be the concept development phase and its three subphases, which is the need analysis, concept exploration, and concept definition subphases. This will be followed by the second phase of the system engineering life cycle, which is the engineering development stage, and which has three subphases of the advanced development, engineering design, and integration and evaluation subphases. The third and the final phase is the post production phase and its two subphases of production and operation and support. We will also be going through some of the challenges that were faced during the development of the GPS. And lastly, we will also go through a brief summary of the entire project and the lessons learned. This will be followed by a quick Q&A session and going through the references that I've used to prepare this presentation. So let's begin. So let us begin. We all know that engineering is the application of scientific principles to design, develop, improve existing structures, manufacture processes to solve problems which improve lives. We also know that a system is a combination of interrelated components, and system engineering is the engineering of such a system. But in today's time, systems are getting more and more complex as different individual components get more and more complex and the relationship between them gets intricate. So, we have a concept of systems engineering, which is an interdisciplinary field of engineering and engineering management that focuses on how to design, integrate, and manage these complex systems over their life cycles. System engineering provides facilitation, guidance, and leadership to integrate the relevant disciplines and specialty groups into a cohesive effort, forming an appropriately structured development process that proceeds from concept to production, operation, evolution, and eventual disposal. So, one can say that it considers both the business and technical needs of customers with the goal of providing a quality solution that meets the needs of users and other stakeholders, is fit for the intended purpose in real world operation, and avoids or minimizes adverse unintended consequences. Let us now briefly see what a global positioning system is. The global positioning system, i.e., GPS, is a radio navigation system which is satellite based. It provides users having receivers the ability to correctly determine three dimensional position, time, and speed information on a global level. This system was developed to help United States of America and its Department of Defense with worldwide position, navigation, and timing functionalities to support military operations such as improved air, ground, sea warfare. However, the main reason for which it was approved was due to its functionality to locate and report nuclear detonations anywhere near or on Earth, sea, atmosphere, real time, thus also making it a nuclear detection system. This system was made available to the civilians in 1983 by US President Ronald Reagan. Each of the GPS satellite continuously transmits precise signals at two L-band frequencies, L1 and L2, where L1 is at 1575.42 MHz and L2 is at 1227.6 MHz. Whereas there is a third L band frequency, which is the L3 specific frequency for nuclear detonation via space ground subsystem on S band. The GPS consists of three parts. First is the space vehicle, which consists of 24 satellites in space, including three spare satellites. There is a constellation of six equally spaced orbits, and each holds four satellites. The three spares are in each alternate orbital plane. Each of these 24 satellites have a 12-hour orbit. The second part is a user equipment. The user receives and compares the time of a signal sent by a satellite to the time it receives it. This time difference, combined with the location of the satellite, allows the receiver to determine the location of the receiver, that is the user. Third is the control station. The control station sends commands, controls, and system data to the space vehicle. It also tracks the space vehicle and monitors its health or condition. In this slide, we can see the various applications of the GPS, ranging from military use to nuclear detonation detection and use by civilians for navigation. In the late 1950s, there were several efforts being put into space exploration and applications. After the Russian Sputnik launch in 1957, Dr. Geiser and Wiffenbach at Johns Hopkins University conducted a research study on the signals generated by the Sputnik satellite. They found that the frequency of the signals sent by Sputnik increased as it approached and decreased when the satellite moved away. This, in physics, is the Doppler effect. This helped them to track the movement of satellite from Earth. This idea was then extrapolated to see if tracking the movement of an object on Earth from the satellite, that is, position distance from the satellite, via same frequency shift was possible. And it was. The Advanced Research Projects Agency, or ARPA, used this to develop the first and initial GPS, which was the transit satellite. This was the first satellite that was launched in 1960. Aerospace Corporation was holding studies for space-based concepts. One of these studies, known as the Project 57, envisioned the use of satellite for enhancing navigation for fast-moving vehicles in three dimensions. It was from this study that the concept for GPS was born. This project eventually became Air Force Project 621B in 1963, which evolved from the previous transit satellite into the current day GPS. Now, before diving into the different system engineering phases of the GPS, let us briefly state each of them. The V model, which we can see in this slide, is a common graphical representation of the systems engineering life cycle. The left side of the V represents concept development and the decomposition of requirements into function and physical entities that can be architected, designed, and developed. The right side of the V represents integration of these entities, including appropriate testing to verify that they satisfy the requirements and their ultimate transition into the field where they are operated and maintained. Let us now see how these phases came into use for GPS. Let us now see the first stage of the system engineering life cycle, which is the concept development stage. This stage questions and answers the need for a new or replacement system. It involves analyzing and planning the new or improved system and its feasibility. And thus, this requires to take into consideration various factors such as stockholders' needs, practical feasibility, budget cost, scalability, etc. Since this is an initial stage of the system engineering or development life cycle, it is very different from the rest of the stages. Systems engineering helps in converting operational needs into an economically and technically viable solution. It can be further classified into three substages: need analysis, concept exploration, concept definition. We will see how this crucial stage of software engineering was carried out while developing the GPS. the concept development stage of the GPS will provide some crucial information needed to carry out the subsequent two parts of the software engineering system life cycle. The primary objective of need analysis stage is to show that there is a valid operational need and a strong market for the new or updated system. Developing this system should bring additional value to its predecessors and should be within an affordable budget with a sustainable level of risk. A need analysis system can be further classified into two types: a need driven system, B, a technology driven system. A need driven system focuses on replacing a system that has evident deficiencies, whereas a technology driven system focuses on developing a new system that is better than the existing ones. Since the GPS development used US taxpayers' money, it was all the more essential to prove to the stockholders the value it brings in for both military and non military use. The 1960s saw the United States Navy conducting experiments to track submarines carrying nuclear missiles using satellite navigation transit. Five satellites were orbiting the poles, and with this, it was possible to observe the satellite changes in Doppler and find the location of submarine every 1 hour. However, this system was not very robust and stable and was slow considering the advancements in the military and civilian automobile industry, which was thriving with fast paced vehicles. Thus, the development of a more robust and stable satellite system was seen as a need and technology driven effort. There were other similar systems developed during this time frame, such as the Timation satellite in 1967, which used clocks accurately in space. There was the Omega navigation system, which was a ground based system based on comparison in phases of signal transmission from pairs of stations. However, due to scalability and accuracy limitations in all these systems, and with advancements in the military and civilian automobile industry, there was need of an equaling solution which was more accurate and universal. There was another need based aspect behind GPS. Around this time, post World War II, there was a Cold War between US and USSR and its allies, and this led to an arms race. The USSR was already a nuclear power, and this posed a threat to the United States. The GPS could also be used to detect nuclear activity near the surface of the Earth, and this was the main reason that convinced the US Congress to spend billions of dollars of US taxpayer money on GPS development. Here we can see some images of the predecessors of the GPS satellite, which was the Timation satellite, the Transit satellite, and the Omega transmitter of the Omega satellite. All these were used as learnings for developing the GPS. Let's now move on to the concept exploration subphase. This subphase uses the output from need analysis subphase and builds on top of it. It converts the operational viewpoint of system to an engineering viewpoint required in all system engineering phases. This means to provide a measurable basis for selecting a system concept that can be evolved into a physical model of the system. Here, the various requirements such as operational, performance requirements are analyzed and a new system or model is selected. Needs driven system development is conducted by the customer itself with maybe the guidance of a systems engineer employed with the customer. Whereas technology driven systems is developed by a system developer skilled in that particular technology. In short, produce a set of achievable performance requirements that are capable to create a system that can satisfy valid operational need. With the help of this diagram, let us now try to understand the steps of the concept exploration phase. The first step is the operational requirements analysis step. It involves analyzing the operational requirements of the system in terms of objectives and then refining them. The next step is the performance requirements formulation phase. and that translates operation requirements into subsystem functions and formulates the performance parameters. After this is the implementation of the concept exploration step. It involves researching all the implementations possible of technology and also defines the performance characteristics. And lastly is the performance requirement validation phase. After about all the steps are done, lastly, as part of the concept exploration phase, integration and validation of the performance characteristics defined in the previous step are done. Let's now see how this phase was carried out in the development of GPS. The first objective, even before analyzing the operational requirements, was to determine the preferred user equipment designs and validate life cycle cost models for the design to cost process. Six classes of designs were analyzed with the aim to have the highest degree of similarity between these designs. This was done as part of the requirements analysis since each design catered to different requirements such as accuracies, dynamics of user, immunity levels to jamming, usage entity, etc. After this, operational requirements were analyzed by testing of operational utilities, demonstrations of coordinated bombing, terminal navigation, landing approaches, army land operations, airborne fueling, anti jamming margins, satellite hardening, etc. was done. Post this, two key performance requirements were established: A. Dropping 5 bombs in the same hole, B. User equipment or receiver for less than $10,000. The first performance requirement, which is dropping 5 bombs in the same hole, helped to confirm the integration of receivers on platforms and the ability to transmit exact space based timing and navigation data. The demonstration of this provided strong data to gain support for the military use of the system. People experienced in the relevant and appropriate fields were required to observe the experiment and review the data for this experiment to gain considerable value. The second of the user equipment cost. The US government, apart from seeing it only as a system useful to detect nuclear armory and used by the military, foresaw its use for the civilian community. Also, by involving the civilian community, it hoped that the commercial market would become competitive, which could benefit the Department of Defense with cost of the equipment going down, which would also in turn be beneficial for the military. Another benefit would be with the vested interests of the civilian community, there would come much needed political gain to keep the program going. Now, the top level requirements were negotiable, and this turned out to be a huge benefit since it allowed the requirements and thus, in turn, the system to keep improving with time and as technology evolved. Requirements were communicated to the stockholders, such as the Department of Defense, operational users, and by doing so, it helped to optimize the operational concept, risk, cost, schedule, performance, and design. Let's now move on to the concept definition substage. This phase involves choosing from a number of alternative or candidate system concepts discussed in the concept exploration substage before. A system that will form the basis of the next stages of development and engineering. This phase actually marks the start of effort for the functional physical characteristics of the new system to be defined. The system development phase will use this to actually develop the new system. To make a final selection, a number of trade studies need to be conducted amongst all the options to assess the relatively better option based on operational performance and compatibility, program cost, program schedule, and risks. Let's now see how this was carried out in case of GPS. General Dynamics in July 1974 performed a series of trade studies on various important requirements listed in the previous phase and selected the relatively best alternative from all available for each requirement. Some of them include the satellite memory loading, satellite orbit, monitor station sites, etc. Now, for the concept For the constellation development in 1974, POC had 6 blocks in the first phase of the satellite in 2 planes and built up to 24 Block 2 satellites in 3 planes. However, there was a consensus that a trade study should be conducted to reduce the number of satellites required by determining a higher SV orbit. JPO, in association with Aerospace Corporation, conducted various analysis and trade studies on working constellation concepts that required in a baseline configuration of 8 satellites, each in 3 circular rings with 63-degree inclinations, with considerations to satellite replacement issues, location of remote sites, and global coverage. Another trade study was carried out for the PRN signal structure. It was one of the most important technologies that has enabled GPS. It too resulted from extensive analysis and trade studies based on system engineering concepts. The structure is based on the ability to communicate accurate timing and navigation data to each of the segments. Substantial trade studies in signal and communications message development were performed to come to this phase from its predecessor project 621B by Aerospace Corporation and Magnavox. There were also some risk mitigations that were done. GPS concept was based on a highly reliable atomic frequency standard or AFS. It was one of the key technologies in making GPS viable. The atomic clocks in the GPS satellite were important in providing GPS users accurate velocity, position, and time values. However, the ability to test these AFS or clocks performing correctly in a space like environment and outputting precise timing to the user receiver equipment was a huge risk. Testing of this feature was done using the Navy Timation satellites, which had atomic clocks on board and incorporating predecessor project 621B code generators. The objectives of this NTS concept development tests were to test the techniques for high resolution satellite orbit prediction, behavior of accurate clocks in space, the distribution of precise time data worldwide, and the signal propagation characteristics. Now let's look at the engineering development stage. The engineering development stage is the second major phase of the systems engineering process and comes after the concept development stage. It involves working on top of needs which were analyzed and finalized in the previous stage. In this stage, we will put together the engineering design and develop the system by first creating a prototype for the system and follow it by rigorous testing until it is deemed perfect for production use. This stage can further be divided into 3 substages. The first one is the advanced development stage, the second one is the engineering design substage, and the third is the integration and evaluation substage. We will now be going through each of these subcomponents in detail and see how they contributed to the development of the highly complex and successful system of the GPS. The GPS engineering development stage aimed to develop the space vehicles, finish the initial operational test and evaluation of the user equipment, and to also begin the production of the low cost user equipment while establishing a two-dimensional limited operational capability. The diagram on this slide shows us the interrelation between the 3 substages of the engineering development stage. It shows how the system functional specifications and defined system concepts from the concept development stage acts as input to the advanced development substage, which outputs the system design specifications and a validated development model, which now acts as the input to the engineering design substage, which then outputs the testing and evaluation plan and the engineered components, which acting as input to the final integration and evaluation stage result in a system with a proven and tested specifications and a production ready system. Let's now look at the advanced development substage. This substage aims to solve the risks associated with the system which were analyzed in the previous stage by performing analysis, development, and validation of the system design, which forms the basis for the full scale engineering process. The result of this substage is validated system design specification and a development model. The need for this subsystem is mainly for systems which have unproven concepts in order to discuss and either prove them or remove them. Now let's look at the different steps that were followed by the GPS system engineering team as part of the advanced development. The first one is the requirements analysis. There were a bunch of requirement analysis that were done. Let's discuss the interface requirements. Now, when the ICS, that is the interim control segment, was being deployed, there was an interface issue with respect to the telephone communications with the sites remotely located. The government and the contractors did not anticipate the issue with the relatively small telephone companies on the west coast of the United States, establishing unique out requirements procedures that influence the efforts to try and determine communication links among the remote stations and the master control and test facilities. And thus, the solution to this was huge workarounds and time intensive solutions. The next were the performance requirements. Rockwell International, which was a parallel organization to the JPO, which was the main organization and tasked with the development of the GPS, along with the JPO, worked on the top level performance requirements for the main component, that is the space vehicle. Now, the performance requirements were the space vehicle life, error budgeting, signal generation, and other some requirements. Now, these interface and design requirements sometimes drove the system level requirements. Design studies were conducted to establish the best way to implement such decisions. Solutions were formulated such that its implementation would minimize the cost and schedule impact. Now, the third type of requirements was the IONDS requirements. These were the interface between the IONDS and the SV or the space vehicle, which required the development of firstly the L3 signal, which was odd to the IONDS data transmission, and secondly the establishment of the ICD and MOA with the Department of Energy, specifically the Sandia National Laboratories and Los Alamos Laboratories, which was done to resolve all the issues. Prototyping. Again, there were the receivers, that is the user equipment, were actually prototyped. So let's see how. The build and validate prototype receivers or the user equipment, which could precisely predict location using time and navigational signals, were made. Performance limits under dynamic conditions in a severe environment were also established. It was essential to perform this in order to ensure that the instruments being developed were actually going to work with the satellites. Using 4 ground-based scrutinized transmitters and the prototype receiver, a test plan was devised and conducted to test the compatibility with the receivers signal-wise. Azimuth and angular errors were scrutinized. This was an essential test for the Phase 1 satellites. As part of risk mitigation, the ability to test the AFS or the clocks, which were of utmost importance in the functioning of the GPS, performing correctly in a space-like environment and outputting precise timing to the user receiver equipment was a huge risk. Testing for this feature was done using the Navy Timation satellites, which had atomic clocks on board and incorporating predecessor Project 621B code generators. The objectives of this NTS concept development tests were to test the techniques for high-resolution satellite orbit prediction, behavior of accurate clocks in space, and the distribution of precise data worldwide, and the signal propagation characteristics. And the testing efforts of the user equipment were also done. A threat assessment study was conducted by Aerospace Corporation for the user equipment receivers, and using the results of which the JPO conducted its own assessment of the 2 types of antennas which were to be used in the receivers. First one was the FRPA or the fixed reception pattern antenna, and the second one was the CRPA or the controlled reception pattern antenna. To understand how a common antenna can satisfy all the requirements of the user and at the same time be cost effective by procuring large amounts of units, After this analysis, the FRPA was finally selected. And lastly, was the functional analysis done. The GPS project funding became a cause for major concern during the 1970s and 80s. System engineering development principles were used to reduce the number of satellites needed from 21 to 18, which in turn reduced costs. Following the systems engineering process, trade studies were conducted on the space vehicle constellation to establish the minimum number of satellites required. The result of these efforts was the decision to have a 18 satellite constellation which would provide continuous global coverage. Below, we can also see how the advanced development substage fits between the concept definition phase and the future engineering design phase. Building on the prototype model derived from the previous advanced engineering stage, this stage aims to create a more engineered prototype with well defined test requirements. In other words, any unknowns arisen from the previous prototype stage model are solved in this stage. Rockwell, which was the organization parallel to the main JPO, which was also working on designing and developing the GPS system, also involved in the engineering design phase. Focus was kept on keeping the design simple so that the manufacturing becomes easier, and also in case of high risk components, addressing the functionality becomes simpler. Four high risk items were designed: the navigation payload, atomic clocks, antenna, and lastly the high power amplifier or the RF chain. Design, fabrication, testing of these components was done prior to contract award so that the risk was reduced and feasibility was demonstrable. The goal for the GPS team during the design and development phases was to construct what was the resultant phase of the previous proposal phases. This policy made sure that the final product quality kept improving during the short factory to launch pad schedule. The triumphant GPS satellite design was the consequence of the below engineering concepts. First, focus was put on the design of the environmentally significant component, which were the atomic clocks, and this made all the component considerations secondary. Design of the GPS system was kept as simple as possible, and that made the satellite highly reliable, cost effective, more producible, and compatible with any other constraints. This simplicity and complexity was extended to the other launch and orbit operations as well. Subsystem designs and trade studies also contributed to the simplistic and reliable design of the GPS satellite system. Some cases of these include the solar arrays with the single degree of freedom drives, which were utilized, whereas the second degree of solar array freedoms were not, since yawing was to be utilized. The less expensive TWT, that is the travel wave tube solid, was pitted against the state HPAs for improved life, removal of high voltage power supplies, and effective power consumption. Onboard systems controlling the navigation functions were no longer required. Passive thermal control systems, which were developed for the temperature sensitive clocks, were helpful in reducing the power consumption. SSR, that is the spread spectrum ranging, and DDSR, that is the data stream signal structures, were optimized in order to meet the link requirements, and strict adherence to the limitations of the national and international regulations concerning EM, that is the electromagnetic radiations, was ensured. Single space vehicle broadcast coverage was capitalized by constructing the L2 array antenna, which was helix phased. This was not only decreasing power consumption, but also from the SV's line of sight was a more analogous radiation pattern was provided to the entire Earth's surface. Magnetic momentum dumping of the ACS, that is the active control system reaction wheels, to ensure long spacecraft orbital life was also implemented. We can see in the diagram on this slide how the engineering design takes input from the advanced development substage and produces output which the integration and evaluation substage, which is the next substage, uses. Post the engineering design phase comes the integration and evaluation substage, which is also the final substage of the engineering development phase. A system engineer in this stage works to determine how closely the system matches its intended design and use cases. The results from this stage are weighed up against the operational requirements which were initially defined in the needs analysis stage. This stage can be skipped if all the components in the system are flawlessly engineered and their designs were perfectly implemented, which would make the evaluation and integration effortless. However, if not skipped, this stage can be a lengthy process. But however thoroughly the components were tested, there always occurs some unforeseen issues that only arise when the entire system is brought together. The JPO, that is the organization which mainly managed the development of the GPS, made sure none of the partner organizations received the responsibility of the system integration. One of the most important aspects in terms of system integration was the control of the interfaces. By taking care of this, it would ensure that the inputs, technical requirements, system testing, constraints associated with all the stakeholders, such as the contractors, US government, etc., were considered equally and in an orderly manner, and at the same time establish a means of communication amongst them. The integration role required communication between the multiple US government and industry contractor companies. This phase involved a lot of fluidity among the different organizations. We can see in this slide how the JPO managed to maintain a communication between the multiple stakeholders. This phase involved a lot of fluidity among the different organizations, which can be seen in this diagram. The program was divided into three separate contracts, one corresponding to each of the three major segments, that is, the space vehicle, the control segment, and the user equipment. The post development stage is the final stage of the system life cycle. This stage commences after all the engineering development validation of the new system is completed. The system engineer performs a crucial role in this stage as many components of the system may demand frequent changes, upgrades, or maintenance even after the development. This stage can be further broken down into two substages: A. The production substage, B. The operation or support substage. The first subphase of the post development stage is the production phase. It aims to incorporate the design and engineering from the previous engineering development stage into real components. This is usually done using a combination of hardware and software implementations. In this stage, the system engineer needs to ensure that the system to be produced needs to be successfully transitioned from the development to the production phases and at the same time meet the requirements for safety, reliability, and affordability. The objectives of this stage for the GPS software engineering team were to fine tune the loose ends of the previous development stage while issuing production contracts for the 28 space vehicles. An initial analysis of the operational capability was performed for a mix of Block 1 and Block 2 satellites, alongside full operational capability for all the Block 2 satellites, and it was concluded that the space vehicles were to be launched from the space shuttle. Let us now look at some of the production stage scenarios for the GPS system. The first one was the space vehicle acquisition strategy for production. JPO, the organization mainly tasked with the GPS development, procured the space vehicles like an aircraft system, which was a new approach for the space community. The concept of this strategy was to buy a lot of the space vehicles, as not only was it cost effective but also a technique that minimalized the approval cycles through the US Air Force, since it was a simultaneous effort in both developing the system and including them into the production contract. The Air Force also gave a fixed price contract to the aircraft manufacturers. McDonnell Douglas was chosen as the aircraft manufacturer to purchase the 28 boosters required for the upper stage, called the payload assist modules. The second example was that of the nuclear detection system. The NDS helped to provide a Earth-wide functionality to detect and report nuclear detonations of any kind that had happened in the atmosphere of the Earth or in near-Earth space in near real time. The GPS was thus the best system to carry this capability, as the GPS baseline was demanded worldwide coverage for navigation purposes. The NDS sensors were developed by Sandia National Laboratories and the Los Alamos National Laboratory and provided GFE to Rockwell. After the first development, the systems engineering process saw a technical risk of integrating one of the sensors, and then the Air Force established a requirement to scale up the IONDS systems, which we saw some while ago. Let's now look at some of the important components of the GPS. Let's talk about the control segment. Based on the control segment functional requirement study done in the earlier phases, five bidders were awarded contracts to perform concept design studies before one was selected to actually pursue the production of this control segment. Multiple rounds of these contractual efforts not only help size down the bidder size but help further develop and refine the concepts and functional requirements, resulting in a pre SDR functional baseline stage. IBM was the final winner of the contract. Although IBM did not have previous experience working in space related projects but had pretty strong systems engineering processes, IBM approached the production with parallel paths. The two paths that it chose was A. Program management and B. A tech group reporting to the director of the program. Originally, the estimate of the size of the control segment software was 300 to 400,000 lines of code. However, the final size of the code reached 1.1 million lines of code. Earlier software releases of the control segment allowed the operation ability to be achieved by 1985. 1986 to 1989 saw a period of software improvements and fault resolution. The second important component of the GPS, which was the user equipment. Now let's see something about that. The late 80s and 90s saw the improvement of the huge and importable user receiver instruments into more portable and simple to use designs. They were basically the commercial designs that were made by companies of these instruments. The Army purchased commercial SLGR, or the small lightweight GPS receiver, for demonstration only, and over time, after a series of trade offs, agreed to incorporate these as part of its man packs. The reason for these changes was to obtain a system more like an off the shelf item that would meet minimum yet critical requirements and be available in the near future, be cost effective and easy to operate. It was established that the commercial products might not match the performance of the top notch AN or the PSN 8 man pack, but nonetheless, it was a viable solution and it worked. We can see the diagram in this slide how it represents the outputs of the engineering development stage, which is the product specifications and the production ready system, and how it behaves as the input for the post development system, which outputs the operation and maintenance documentation as well as a fully functional and installed operational system. The second component of the post development stage and the final component of the entire system engineering system life cycle is the operation and support phase and marks the end of the role of the systems engineer. The aim of this subphase is to provide support and maintenance to the system post its deployment in the field in order to sustain the life cycle of the product. To do this, there should be a well structured plan for the maintenance, timely upgrades, and repairs, if any, of the system that is expected on any product as it wears over time. The Global Positioning System, aka the GPS project, was envisioned and started out as a vague new idea post the launch of Sputnik 1, when it was realized that space frontier can be used for many exciting opportunities. Navigation studies and technology attempts caused a functional baseline to be set up around 1973.
To have a more stable, accurate, and reliable means of worldwide navigation. On 17 April 1995, nearly 20 years later on, the US Air Force Space Command declared the GPS fully operational. This accomplished US Department of Defense's major goals of uniting suites of various military navigation systems. As part of the fully operational capability, the system was triumphantly tested in battle in the Persian Gulf War years before the IOC, that is the initial operational capability, which proved its operational capability worthy to the visionaries of the program from the late 1960s. The JPO, which was instrumental in the development of the GPS, was able to successfully establish themselves as system integrators and controllers of the functional baseline. Furthermore, with the assistance of the Aerospace Cooperation, JPO was able to conduct required system trait studies in order to optimize the functional baseline, from which increased requirements were identified, resulting in changes in future budgets. Baseline structured signal was used as the vital interface to create a specification tree which was based upon the alliance of the signals associated with the three major components of the GPS, which allowed to manage all the system integration and segment specifications. Domain prowess existed on all levels with the other contractors and supporting government agencies, which allowed visibility into the system vision and thus the systems engineering process a success. Communication was seen as a vital ingredient that was encouraged throughout the GPS development.
Let us now look at some of the challenges that were faced during the GPS development. Rockwell GPS Block 1 satellites clock. One of the major challenges was during the development of the Block 1 satellites by Rockwell, which involved developing a space qualified clock based upon the research data and lessons learned from previous Timation and NTS programs. The original plan for the Block 1 satellite was that each satellite would contain two rubidium and one cesium atomic clocks after SVN 3. However, three rubidium clocks were flown on SVN 1, 2, and 3, and two rubidium and one second generation pre production model clock was incorporated after SVN 3. The C clocks was referred to as a pre production model and was derived from the NTS 2CS clocks. The high level requirements were clock stability and a service design life requirement for 5 years. Embedded in the service life requirement was the ability to withstand the space environment, especially thermal and radiation effects. NRL had adequately addressed the radiation effects on the clocks in the earlier phase of this program. The second challenge was for Rockwell during developing the atomic clocks, which was also the rubidium lamp, which was a high risk effort. Rockwell got technical expertise from Aerospace Corporation to resolve issues with the lamp. Diligent testing with actual hardware was conducted to verify radiation, thermal, and life cycle requirements.
Let us now look into the summary and lessons learned from the GPS project. During the development of the GPS, the team faced interesting challenges in a bunch of domains, such as the stakeholder expectations, organization, technology, budgets, and scheduling for the very complex navigation system. However, the results paid off as this system was a huge success to the civilian, military, and other related unique applications, and it became a beacon. A constellation of lighthouses in the sky can be the best analogy for it. An amalgamation of varied principles, fundamentals, followed by the global positioning satellite program is one of the reasons for its success. And these principal foundations are educational for contemporary programs because they provoke thought in those who wish to scrutinize the programs. That being said, these foundations are, of course, a complete set of necessary or sufficient conditions. For the implementer, the successful and consistent application of all the systems engineering processes discussed above are required throughout the program and project execution, starting from the conceptualizing the idea to its usage and right to the eventual disposal of the system. Highly experienced and skilled system engineers applying the correct system engineering process, principles, and tools are essential in each and every step or stage of the process. Systems engineering is strenuous work. It requires skilled and well learned engineers and managers who have a forward looking vision to the program with an eye for detail. As we saw throughout this case study, we can conclude by saying that systems engineering played a vital role in the program's success. The challenges of identifying requirements, building and using a system of systems approaches, amalgamating new technologies, dealing with the abundance of government and industry agencies, and most importantly, dealing with the absence of an available working user in the nascent stages of the program were achievable due to advanced, powerful, coherent, established systems engineering process. The GPS program embedded the systems engineering concepts in their goal, database, and generally in their day to day practice to make sure that continual and proper system requirements are identified. Allotment of these requirements to the completely autonomous segment developments and furthermore to the subcontractor or vendor level. The continuous assessment based improvements of new requirements, unconventional test methods to check the actual design performance against the requirements, operations or missions analysis, a budget analysis to support the need for the program, and a powerful system integration process. The program was thus able to completely abstain from major risks due to the acquisition strategy, trade studies usage, premature testing of the conceptual designs, subject matter expertise, and a holistic perception of the program from both the contractor and government ends.
I would like to thank Professor Konyan Zhu for his guidance and his lecture material that helped impart knowledge of system engineering to me, which helped create this report. And I would also like to thank our TA Yunfai for her patience with my queries. Thank you for being a patient audience and being with me till here. Feel free to ask me any questions by emailing me on the below email address. This slide includes all the references that I have used in preparing this presentation. I would like to extend a sincere thanks to all the people who have contributed in these links. I would once again like to thank you for being a patient audience and for being with me till the very end. Have a good day.